Hello, welcome to Lesson 11, Discrete Distributions, Bernoulli, Binomial, and Hypergeometric. Some introductory examples here. If a coin is flipped 100 times, what's the expected number of heads? It's 50. If a die is rolled 100 times, what's the expected number of twos? It's 16.67, rounded off. So in general, for this type of situation, the expected value is n, number of trials, times the probability of success. So in the first example, it's 100 times a half is 50. In the second example, the probability of rolling a 2 is 1/6. It's 100 times 1/6. So in general, when you have a binomial random variable, the expected value, E of x, is going to be NP. And we're going to work our way through where that formula comes from. So we start out with the Bernoulli distribution, and then we'll look at the binomial. So the Bernoulli, we have basically a single trial, two possible outcomes here for x. It's probability P that x is 1, and 1 minus p for x equals 0. Everything else, the probability is 0. So the only values that x takes on are 0 and 1. The probability of x being 1 is p. The probability of 0 is 1 minus p. And p is somewhere between 0 and 1. So what's the expected value of a Bernoulli random variable? So we use the formula, summation x sub I, p of xi. The only x values here are 0 and 1, and we multiply with their probabilities. So it's 1 times p plus 0 times 1 minus p. It should be 1 minus p. So 0 times anything is 0, and we're left with 1 times p, which is just p. So the expected value of a Bernoulli random variable is p, the probability of success. Now, what's the variance of a Bernoulli random variable? We need to do the expected value of x squared. So that's going to be 1 squared times its probability p plus 0 squared times its probability, which is 1 minus p. And again, the 0 knocks out everything, and we're left with 1 times p. So we get the same answer. We get p again. So now we do the formula here for variance, expected value of x squared minus e of x squared. So it's p minus p squared. And if you want, you can factor out a p times 1 minus p. So summarizing, for a Bernoulli random variable, the expected value is equal to p. The variance is p times 1 minus p. Now we can view a binomial as a sum of Bernoulli, but we'll recall the criteria for a binomial. You have a fixed number of trials, n. The probability of success in a single trial is always the same. It's p. And there are two outcomes. The trials must also be independent. So what happens on one trial has no impact on any of the others. But we can consider a binomial as a sum of Bernoulli random variables. It makes the calculations a lot easier. So if we think of a binomial random variable as a sum of n Bernoulli random variables, then the expected value is just the expected value of a sum is the sum of the expected value. So we just repeatedly add up the expected value of each, and that's p. So we have n copies of that. So the expected value of x is n times p, which we mentioned up at the beginning there. For a binomial situation, the expected value, expected number of successes is NP. Now the variance. Assuming independent trials here, the variance of a sum is the sum of the variances. Now the variance for the Bernoulli was p times 1 minus p. So we have n copies of that, repeatedly adding, multiplied by n. So the variance of the binomial is np1 minus p, or sometimes written as npq, where q is 1 minus p. Q is the complementary probability. Q is the probability of failure. It's the opposite of p. It's 1 minus p. The standard deviation is the square root of the variance, so we can write that as root np times 1 minus p. Now I'm going to briefly go through the direct proof for the mean of the binomial. It's a lot longer than using the Bernoulli viewpoint, but this technique will be used for other types of variables, so it's worth getting a look at it here. So we take the binomial distribution. Probability that x is equal to x is n choose x, p to the x, q to the n minus x. X goes from 0 to n, q is 1 minus p. And we look at the formula here for expected value. It's E of x is summation x times p of x. So we're multiplying x times the probability mass function here for the binomial. So it's n choose x, p to the x, q to the n minus x. X goes from 0 to n. Now notice that the first term is going to be 0. The starting term is going to be 0 because if x is 0, then the whole thing is 0. So we could skip that. We can skip that term. Now what happens when you multiply x times n choose x? N choose x is n factorial divided by x factorial times n minus x factorial. We're multiplying this whole thing by x. The x is in the numerator. It's going to cancel out here with the leading term in x factorial. X factorial is the same as x times x minus 1 factorial. We can cancel out the x's. So x times n choose x becomes n factorial over x minus 1 factorial times n minus x factorial. Now, it turns out that this is the same as n times n minus 1 choose x minus 1. So what's n minus 1 choose x minus 1? It's n minus 1 factorial on top divided by x minus 1 factorial times the difference factorial, n minus 1 minus x minus 1. Now, doing that subtraction, the ones are going to cancel out, and we're left with n minus x factorial. Multiplying this extra n, we get n times n minus 1 factorial, which is n factorial. So we're left with n factorial over x minus 1 factorial, n minus x factorial, which is the same thing that we got up here. So we've shown that x times n choose x is the same as n times n minus 1 choose x minus 1. So we can substitute that into this expected value expression. So we can replace x times n choose x with n times n minus 1 choose x minus 1. Now n is fixed in this sum. The sum is depending on the value that x is at. So we can factor out the n, and we can factor out one of the p values. And a little bit of technical detail here, but what's left is essentially the sum of all the possible probabilities of a binomial, and that sum has to be one whole or 100%. So this entire thing is going to be 1, and that leads us to the value of NP. So I'm just going to briefly summarize here, but the reason this sum is 1 is because it's the sum of all the possibilities of the probability mass function, which has to be 100% or one whole. So we make a little bit of a technical shift here, calling y equal x minus 1. X would be y plus 1, and substituting that in. And you can view this as a binomial PMF. We have the sum of all the probabilities of a binomial random variable y with n minus 1 trials, probability of success p. So again, getting that viewpoint, that gives us that this entire expression is just np times 1, which is np. Again, for the binomial, the way to go is a sum of Bernoulli, but we will need that technique in some other situations. All right, let's do a numerical example here. This is from the text 4.40. On a multiple choice exam with 3 possible answers for each of the 5 questions, what's the probability that a student will get 4 or more correct answers just by guessing? So this fits the criteria of a binomial random variable. We have a fixed number of trials, 5 questions. The probability of guessing correctly is 1/3, and that will never change. The guesses are independent. And the number of successes we're looking for is 4 or more, which is 4 or 5. Even though there are 3 possible answers, we can view this as 2 outcomes, either correct or incorrect. So n is 5 trials, 5 questions. The probability of success is 1 out of 3. There are 3 possible answers. We're guessing, and one of them is correct. So that's 1/3. Q is the opposite, the probability of failure, of getting it wrong, 2/3. And X is the number of successes. It's either, we have to do 2 cases here, 4 or 5. So we do the formula twice. So X equals 4, we get 5 choose 4. 1/3 to the 4th, 4 correct, 2/3 to the 1st, 1 incorrect. And then we do the next one, which is 5. It's 5 choose 5, 1/3 to the 5th, 2/3 to the 0, and that's 1 out of 243. So we want the probability of getting 4 or more correct. So that's greater than or equal to 4. The probability that X is greater than or equal to 4 is the probability of exactly 4 plus exactly 5. So it's 10 out of 243 plus 1 out of 243 is 11 out of 243. Decimal form 0.0453. So low probability. Now, you want to be careful. In general, sometimes it may be easier to count the opposite. In this case here, greater than or equal to 4 stopped at 5. But sometimes you want to look at the opposite point of view. If that's less counting, in this case here, it's more counting. The opposite would be 0, 1, 2, and 3. So that's more than doing 4 or 5. All right, uniform distribution. So you want to be thinking rolling a single die. That's an example we did where the random variable does follow a uniform distribution. So the probability of any value is the same. It's 1 over n for n possible values, and it's 0 everywhere else. So uniform distribution means each element here, each value is equally likely happening here, 1 over n. All right, so expected value, summation xi, p of xi, all the probabilities are the same, 1 over n. The x values go from 1 to n. So factoring out 1 over n, we're left with the sum from 1 through n. So you may have seen this in Calculus 2 or some other courses like discrete math. The sum formula for the first n integers, n positive integers, is n times n plus 1 over 2. And then one of the n's cancels out here. And we're left with an n plus 1 over 2 for the expected value of a uniform random variable. In the case of the die, it's 6 plus 1 over 2, which is 7 over 2, 3.5. I should be careful. This is the formula as long as the possible values of x are 1 through n. If you start at a higher number, a different number than 1, there would be a slight adjustment, but it is similar, though. Now, the variance is expected value of x squared minus e of x squared. So e of x squared, we're squaring each of the possible values times the probability 1 over n. 1 over n factors out. We have the sum of squares here, and that sum is n times n plus 1 times 2n plus 1 over 6. So one of the n's cancels out. It's n plus 1 times 2n plus 1 over 6. Plugging into the formula, we have to do that expression minus the mean squared. And the mean we've just found to be n plus 1 over 2. So squaring the top and bottom there, we get n plus 1 squared over 4. We can factor out an n plus 1 from the numerator. We're left with 2n plus 1 over 6 minus n plus 1 over 4. I'm going to put an extra parentheses here just to be safe. I want to be careful of that subtraction sign. Common denominator is 12. Multiply the first fraction by 2. Multiply the second one by 3 over 3. Common denominator of 12. Distribute through, we get 4n plus 2 minus 3n minus 3. Distributing the negative through. 4n minus 3n is n. 2 minus 3 is negative 1. It's n plus 1 times n minus 1 over 12. N squared minus 1 over 12. So again, that's the variance of a uniform random variable with x values 1 through n. In the case of the die, we had 6 squared minus 1. It was 35 over 12. Hypergeometric distribution. So this is kind of similar to binomial, but the selections are done without replacement. And so that's going to affect the probabilities. We don't have a consistent probability. The trials are dependent. So we have an example here without replacement. Given we have a total of 7 red and 12 blue marbles, find the probability of selecting 3 red and 2 blue. So out of the 12 blue, we're going to select 2. So that's 12 choose 2. And then we're going to fail 3 times. And so that means selecting 3 from the 7 red. And then the denominator is the grand total. There were 19 total marbles, and we're making 5 selections. So that's 19 choose 5. So in terms of a general form here, we have 2 different types of objects, N1 and N2. Their sum is capital N. We're making N selections without replacement. The probability of X successes. So we're going to make N selections here, and we want X successes. So out of the N1, we want to choose X, and then out of N2, we're going to get the remaining amount, N minus X. And then the denominator is the total number of ways to select little n from capital N. That's capital N choose little n. And so this is the formula for hypergeometric. So these are combinations. N1 choose X times N2 choose N minus X over N, capital N choose little n. the expected value here turns out to be the same as the expected value for the binomial situation. It's NP, but the variance is different. The variance of the binomial is NPQ. The variance of the hypergeometric is capital N minus little n over capital N minus 1 times NPQ. So the expected value is the same. Variance is a little bit different here. All right, this wraps up lesson 11. As always, if you have any questions, please email.